Thanks, Luca. This is a jam-packed talk, so I'm going to be talking as fast as I can, and we'll try to get through as much material as possible. Like Luca said, this is my talk on type-level programming in Chapel for compile-time specialization. So first, let's talk a little bit about compile-time programming in Chapel. You might have seen a bit of it throughout the presentation, but in general, Chapel has type variables, which, as their name suggests, can be used to store types instead of values. So in this instance, I have a myargs type, which stores the type of pairs int and real. You can also write procedures that take and return types using type formals and the type return intent. Here's an example of such a procedure from the standard library, which takes a type, and if that type is a nillable class type, as a non-nillable class type, makes it nillable by using a question mark. And finally, Chapel also has param variables, which store values that are known at compile time. So I can store the number 3 into a param number of elements, and then use that at compile time to create a new integer of 3 elements. So number of elements times int. Chapel also folds compile time conditionals where possible. So if you have a conditional like if false, Chapel will not bother resolving the code in the then branch because it knows that the condition will always be false, and therefore there's no need to resolve it. But all of this comes with some restrictions that are pretty draconian. So first, compile time operations do not have mutable state. Once you assign the param or type variable, you cannot change it. Also, although Chapel has param loops, which are unrolled, this does not really help you program at compile time because you still don't have mutability. So you can unroll a param loop and resolve its body 10 times, but since you can't change any variables, you can't really preserve any computation between loop iterations. And finally, without state, any functions that accept and produce params or types are basically pure. You really cannot have side effects or like print something to the console except as compiler warnings. But if you say the word pure, you might think of a different language that has that word associated with it. And the language I'll talk about here is Haskell. So Haskell does not have mutable state by default, though you can do some weird things. Haskell doesn't have imperative loops in the traditional sense, and Haskell functions are pure with the exception of some escape hatches. And yet, Haskell programmers are pretty productive. So they achieve this in functional programming languages by using pattern matching and recursion to express their algorithms instead of loops and things like that. So here's an example of a functional data structure of a list. Such data structures are defined by basically listing the possible cases of these data structures. So a list can be two things. Either it can be an empty list, or it can be some element followed by an arbitrary number of other things, encoded as a smaller list. So in this encoding, nil is the empty list. And if you want to encode the list 1, that would be the number 1 followed by the empty list. And then 1, 2, 3 is the number 1 followed by the list, the number 2 followed by the list, the number 3 followed by the list, empty list. And that's written like this. Then when you want to write functions on your data structures, you use pattern matching and recursion. And you basically examine the cases of your data structure. So here I wrote a sum function that takes our list and produces the sum. This function produces 0 for the empty list, and if you have a value plus some kind of remainder of the list, the sum is that value plus the sum of the remainder of the list. So here we have a recursion, and these are the two cases that the function handles. And here's how Haskell evaluates this. Basically, when you write sum 1, 2, 3, which is the list 1, 2, 3 that we saw in the previous slide, it basically picks the appropriate case based on the argument to sum. So in this case, we have sum cons, and we saw earlier that the sum cons case is replaced with I plus sum tail. So in this case, I is 1, and the tail is the list 2, 3. So we get 1 plus sum 2, 3. We do this 2 more times to replace the sub-expressions with 1 plus 2 plus 3 plus sum nil. And finally, the other case in that sum function is that sum of nil is equal to 0. So we replace sum nil with 0 and get 1 plus 2 plus 3 plus 0, which fortunately adds up to 6 as desired. So this picking cases based on arguments is actually very similar to how Chapel does function overloading. So as a very familiar example, suppose you have two procedures, one that takes an integer and one that takes a real number. You then call foo with an integer. And since the argument is an integer, Chapel picks the first procedure to call in this case, and we print int. And a slightly less familiar example, instead of values of int or real, you might accept types. So the first procedure accepts the type integer, and the second procedure accepts a type real number. And actually, there's subtypes of integer and real, but these only have one instance, so it doesn't really matter. And so you can call foo of int, and because the first function matches int, the first function will be the one that gets picked, and you'll get a compiler warning that says int. So this is actually very similar to how Haskell does things. And in fact, you can encode a list in Haskell using Chapel's type system. So like I mentioned earlier, this list has nil and cons, the two constructors. And since in Chapel we're programming at the type level, we want to create types that correspond to nil and cons. For this, I create two records that are effectively empty, the nil record and then the cons record, which has some fields, the head of the list and the tail of the list, like in the Haskell case, but these are compile time values. So in practice, the runtime value of cons is empty. I can then encode that same list 1, 2, 3 by applying the cons type constructor repeatedly. And finally, I can write a sum function that accepts either the type nil or the type cons and returns the appropriate sum. So here, for nil, like in the Haskell case, I return 0. And for cons, I use type queries to extract the head and the tail. This is basically pattern matching. And return I plus the sum of the remainder of the list. And if I then issue a compiler warning, which proves to you that this is actually done at compile time, I can have the compiler print the number 6, indicating that it actually evaluated this code. And although this original program is fairly convoluted or complicated, at least non-trivial, this program becomes at compile time replaced with the number 6. And this indicates that there's actually no runtime overhead to all of this machinery that we did. And so it's just the same as compiling write-len 6 in the end. And now you might be thinking, why on earth did we do this? I've made a robot that screams, but why? Well, there are two possible cases, but in fact, there's even more applications that I'm not going to talk about. For one, do you want to write code that's parameterized and configurable without paying any runtime overhead for the configuration? Sorry, this should say compile time parameters. I had a worked example for this, which is a linear multi-step method approximator that can be configured with various linear multi-step methods at compile time. However, this talk is not long enough for me to show it to you here, so I'll have to skip over it. And furthermore, another worked example is that you can use this feature to create powerful compile time checks on your function's arguments. So a worked example that I will show you is a printf function that's type safe, and this allows you to pass arguments that don't match your format string. Like I said, there's just not enough time to talk about both of these. If you would like to learn about the linear multi-step method approximator, you can read about it on the Chapel blog by scanning this QR code. And now let's move to the type safe printf. So you're probably familiar with printf, and it's a function that takes a string with some placeholders indicated by percent whatevers, like %s and %d, and then some arguments that are spliced in place of these placeholders. So here I have hello %s, your ChapelCon submission is %d, and the string Daniel will be spliced in place of %s, and the number 18 will be spliced in place of %d. And this function will have runtime errors if you write the format string wrong. So if you write %s, but then you give it an integer, or %d and give it a string, you will have problems at runtime. So can we define a printf in Chapel that is type safe at compile time and therefore will not allow you to write this incorrect case? Well, the answer is yes. The general idea, though, is another type level list. What we'll do is take the format string as a param compile time string and extract from it a compile time list of the expected argument types. To make for nice error messages, I'll also have this list include the human readable description of each type, though I recognize in retrospect that this is unnecessary. Finally, I found it more convenient to just redefine lists for various problems instead of using the same list definition over and over, because I can make them more specific to my use case. In this case, I still have a record nil, but this time I added a type level method to it called length, which for the empty list returns 0. And I have cons, which encodes some format specifier and a list of the remaining format specifiers stored in rest. So here, the expected type is the type the user is supposed to pass to the printf function, and the param name is the human readable name of the type that we should print. And then I also define a length function, which is 1 plus whatever the remainder, whatever the length is of the remainder of the list. So here's the first interesting function from this example, which is one that takes a param compile time string and iterates over this string to find all the format specifiers and construct a type level list. So we can't write for loops like I mentioned, for compile time programming. So instead, we use recursion, and I effectively have the index of the loop passed as a recursive parameter to the function. So if we reach the end of the string, there's no format specifiers left to create, so I return the empty list. And then if the first character of the string is not a percent sign, so that's this else case here, then we're looking at a character like H in hello world, and we should just ignore it. So I recurse into the rest of the string, increasing the index. And then the rest of this function is actually the meat of the implementation, where we look at the current format specifier and decide whether or not, or decide what type it should correspond to. So basically, we look at the character following the percent and say, if it's a string, create a list which includes a string. And if it's an integer, create a string that creates an integer, that contains an integer, and so on and so forth. In all of these cases, we recurse into the rest of the string, skipping the percent and whatever the format is, to construct the remainder of the format specifiers. And of course, we allow the user to write double percent to actually insert the percent character into their string. And we emit a compiler error if we don't recognize the format character. So if we give this a quick try, I can call specifiers with that format string that I showed you earlier, and it produces cons string cons int nil, which is exactly the list of one string and one integer, which matches the format specifiers as desired. So now that we have a list of type specifiers, what we want to do is actually validate that it's correct. So the Chapel standard library has a nice is subtype function, which you can use to check if one type is passable to another type, to a formal of another type. And we'll use this. Furthermore, suppose for a minute that the length of our type specifiers matches the number of arguments that the user gave to printf. This is just a simplifying case to write our validate function. And since Chapel doesn't actually support empty tuples, we can also assume that our list of type specifiers and the variadic arguments to printf are non-empty. So given these constraints, we can actually write another function that validates the types as follows. This function effectively recurses by visiting this list of type specifiers. And since it's not as easy to unpack tuples into their first element and the rest of them, I actually use the same tuple type and a param index into that tuple. So basically, we look at the current argument type by indexing into the tuple of arguments, and then we see if that is a subtype of the current format specifier. And if not, we emit a compiler error that says the nth argument, and here being index, was expected to be this thing, but it was in fact something else. And that validates the type at the current head of the list. And then if we have more types to validate, we have to recurse into the rest of the list. You might notice here that to my compiler error, I've used index plus 2 as an argument, and this basically positions the compiler error at a particular place in the call stack. Specifically, the goal is to make this error be emitted precisely where your call to printf is. So if you call printf with the wrong thing and validate gets called recursively like 100 times, this error will get printed next to the call to printf that was invalid. All right, now let's look at the various overloads of this function that we need to make it work. I've named it fprintln for formatted print line because to me that's the most consistent name for this function. So like I mentioned, Chapel doesn't support empty variadic arguments or empty tuples. So for that case, we specifically write a non-variadic function that takes a format string and asserts that this string has no format specifiers, because if you're not giving it any arguments, there better not be any %s's or %d's accepted. So here I use a where clause to say the length of the format specifiers is 0. And in this case, we can just print the string. If the user did provide some format specifiers and some arguments, but didn't give the matching number, we write another overload that specifically emits a compiler error. So in this case, this is an overload which has a where clause that asserts that the number of specifiers does not match the number of arguments. And in this case, we just print a compiler error. And finally, the good case in which the user provided the correct number of format specifiers that matches the number of arguments, we call our recursive validate function starting at 0. And if that function doesn't emit a compiler error, it basically it's an empty function. So it gets elided, and we write the string using the runtime writef functionality, which is now guaranteed to work. Here's a few instance usages of this. I can use fprintln to print hello world with no arguments. That's fine. That prints hello world. I can use fprintln to say the answer is %i and give it 42, which prints the answer is 42. But if I give it a format string that has %i, %s, and the arguments are 1, 2, and 3, it'll say, hey, well, the third argument was supposed to be a string because it's %s, but you gave it an integer. You can't do that. And of course, the implementation I showed can be extended with more format specifiers, more escaping behavior and things like that. But the basic idea is what I showed you. And now let's talk a little bit about going beyond lists. So I've talked about, oh, you can write arbitrary functional programs at the type level. Isn't that amazing? And all I've shown you are lists and recursion, which might be a little bit underwhelming if the speed of this presentation isn't so breakneck. But is that all there is to it? Well, my claim is no. In fact, the kinds of data types that Haskell supports, such as lists, are called algebraic data types. And at their core, they're built up from two operations, Cartesian product of types and disjoint union of types. There's a bunch of others that you need in Haskell to build recursive data types, but we won't need them in Chapel, so I'll skip over this. And here are some words that you know that I know that these things exist and I believe in them. But in fact, my claim is that because Chapel supports disjoint union and Cartesian product, we can actually encode any data type that Haskell can encode. And I believe this claim is true, though I won't be able to give you very precise evidence in this talk. But here's a general recipe. So suppose you have a Haskell data type with a bunch of constructors. For each constructors, you can define a record to introduce a new type with that constructor's name. And for each field in this constructor, you will have to have type fields in that record. And if you have primitive types like integer, you can use params instead of types. So here's a general side-by-side visual example. You can have a Haskell data type which has 1 through n cases, each named C1 through Cn, and each of them has a different number of arguments, arg1 through argi and arg1 through rj. The way to encode this is basically to create one record for each constructor and have type fields for each of the arguments, the constructors. So arg1, type arg1 through type argi. And then I will certainly not have time to show you this, but I've encoded a binary tree using this thing, including insert and lookup operations, which I've arranged to show you the similarity between the Haskell and the Chapel implementation. So, you know, if a value is less than the current node, you recurse into the left node, and if the value is greater than the current node, you recurse into the right node. And then here are the corresponding trees, and you can use lookup, and the cases for the lookup very much match the Haskell implementation. And if you run insert and lookup, you actually get the correct tree. And going a little bit further, you can actually write a key value map by associating not only keys in your binary search tree, but also param values. So in this instance, I actually created a map from the integer value of something to its string representation. So 2 gets the string 2, 1 gets the string 1, 3 gets the string 3. And at compile time, you can perform insertions into this tree and then look things up. And like I said, remember that all of these things are executed by the compiler at compilation time, and therefore you pay no runtime overhead. So you can do pretty much arbitrary Haskell code at compile time in Chapel. And in conclusion, this kind of proves to me and to maybe you as well that Chapel's type-level programming is incredibly powerful. And you can write compile-time programs that are pretty much Haskell programs with a little bit worse syntax. And this makes it possible for you to write highly parameterized code without paying any runtime overhead. And it also allows you to devise powerful compile-time checks and constraints on your code with pretty much arbitrary logic. Whatever you need, you can encode. And this allows for general purpose type level programming, which can be applied to whatever use case you have. And I have some extra slides that didn't make it to this presentation, but it seems like I've come in just in time. So thanks for your time and attention.
Yep, let's thank the speaker with one virtual round of applause. We have 1 minute, so maybe time for one quick question, if there's any from the audience. Yeah, Michael.
Hey, Daniel, that was a really cool talk. My question for you is, do you have any idea how the format string checking impacts compile time? Or is that not measured yet?
I have not measured it in much depth, but it didn't seem particularly slower than just creating write-len in my, non-scientific experiments. So it hasn't been so bad so far.
Thanks.
Alrighty, I yield the floor. Thanks, everyone.